Welcome to Renaissance Charge Videos. I'm Rick Friedrich, and today I'm going to be talking briefly about a couple of additions that we are doing and a couple of reminders of what we've done that go together. And so what I want to talk about, this is my 10 dual pole 10 coiler dual pole Energizer motor, and this one doesn't have the generator coils in it. This is for a customer, that's why I'm doing this video actually. And so I'll go over some basics on the motor for those who don't know, and for those who, there's a couple of people that are assembling this kit, and so this is some of the instructions too. So the main thing I want to go over is the issue of damaging the semiconductors. In this case we're using MOSFETs. We use 3 types of devices with these motors, and for the switching. And so first we use transistors, and the issue with transistors is they take a lot more energy than MOSFETs, so we use MOSFETs now. We also use IGBTs. We haven't sold that, but we've been testing that for quite a while now, and we'll probably be creating some options there. We can go to pretty high voltages. Somebody on the YouTube comments made that comment the other day, and it's true, but they do have some limitations as well. So they behave a little bit differently. So we'll see what we do in the future with IGBTs. But for now, we're talking about MOSFETs, and what we have here is the 2500 watt MOSFETs. And they go up to 500 volts. And so we're going to look at the voltage again. And so one of the problems is there's an internal diode that protects the MOSFET in a sense. Anyway, if you exceed the maximum of that, you can damage the diode and then damage the MOSFET. And a lot of times the heat that you're causing in such systems like this is due to exceeding the MOSFET's voltage ratings with the spike, and then causing the diode to be damaged or heat up, or both. And so what happens is you can damage the MOSFET and the diode and it'll still function. And I've talked about this, repeated this many times, and this is a major concern because if people damage a part and don't realize it, and they get poor performance after that, for example, have bad charging rate at that point, which is, I think, happened to quite a few people over the years, and not realized it, and then they're just not satisfied. But really, you know, you could do that right from the beginning. So what we did to deal with that was put capacitors. Now we're going to add another safety feature, but let's talk about the capacitors first. So across the drain and the source, so the input and the output of the MOSFET, so the center terminal and the right terminal, for those who don't know those terms, we put the capacitor. Now, I'm going to say this again, the capacitance will depend, the ideal capacitance that you put on this will depend upon what voltage and power you're going to run this at. So now, the MOSFET has its own internal capacitance in several different junctions. And when we add more capacitance, in this case we're adding actually 2.2 microfarads per MOSFET, which is rather high, and it's more for higher voltage and higher power that we were going to do that. I think what we're going to do from now on with these bigger kits is we're going to double. I'm going to provide 2 1 microfarad capacitors per MOSFET, and that way you can, if you're going to run it at like what we're going to do right now is 12 volts, then you would run it lower. Now, why would you run it higher or lower? How does it affect things? Well, if we look on the oscilloscope across the same terminals, you'll see that the spike will be quite low with this large capacitance here, and you'll see some oscillation there as well. Of course, we're not running it yet, and I haven't looked at it since I just made this system. I haven't hooked up the oscilloscope yet to it, so we'll look at it together for the first time here. And we've already looked at it in previous videos, but just for this particular setup, this one doesn't have the generator coils on it, so there's no low. It's going to go very fast. I haven't looked at the RPM, but this is like it makes me a little nervous standing beside it, because this is like this very high-speed spinning disc, and you know, it'd be like a very dangerous blade, you know, if you got near it. So anyway, and I have this in self-starting mode, so that should be nice, and I'll talk about that in a minute. But let's go back to the capacitors. So once, so what we want to do is keep the spike underneath the 500 volts with this particular MOSFET. In the little kit, we're limited to 100 volts. It's a better FET, but it's a lower voltage FET, and I say better because it's less resistance and it's got a lot of speed to it for its cost. Now, it doesn't have the total amperage power that this FET does, so they're comparable. But anyway, we want to not exceed the maximum voltage rating of the MOSFET, so we do that with, you know, these capacitance. And now, you know, this is all straightforward information, but what we're dealing with is a lot of nonlinear, extreme pulsing situations here, and so we have to watch these things in different ways. But anyway, we don't want to exceed the voltage, so we want a capacitance at the voltage and the power. As we go up in voltage input, this is the input battery, this is a charging battery. As we go up in input voltage, so 24, 36, 48, then the spike is going to get higher and higher, just the running. And of course, startup is going to be higher power, so you'll see it right at startup. Once you get up to, you know, your settled RPM, unless you're changing your loads on the shaft here, then your voltage is going to, or the voltage is going to come down. So you could put in some switches if you really wanted to get particular about it. Now, the thing about it is, the lower the voltage spike, the less the battery is going to be charging. And so this is not necessarily a bad thing, but because what happens is it circulates the energy within the front end of the motor, so it sends more power back to the input battery, and then it sends it through the motor as well. So the capacitor discharges in a useful way. It's not like a snubber system, which, you know, some of the snubber systems, they do try and recirculate the energy, but not really in a correct way. And what we're doing, of course, different than all motors, is we're charging this battery where the normal snubber system is. So what we're going to do is make sure that the spike isn't too low, So we want to keep it, if it's 500 volts maximum, we want to try and keep it in the 400 range, not too close to 500, because if you then put just a stronger load on it, then it will go higher in voltage. Now, the capacitor will tend to regulate that, but not be an absolute fail-safe. Like if you really load it down, that's when it would exceed. So what I've done is, I've been procrastinating for this for years. Like in the old circuits that we still sell with the little window motor and the fan kit, we have the little neon bulb. And of course that's not suitable for this kind of power levels. And there is no neon bulb that can regulate that spike and keep it down without, with this power level of a system. So, what we're using in the Don Smith systems that we're looking at in the new Don Smith book that I've just finished publishing, and it is starting to ship, by the way, at least for those who are asking, at least not the American orders, because I'm still waiting for those books, but all the worldwide, outside of Canada and the United States, all the books have shipped. So those of you who are waiting, it's a lot of books. Anyway, the other ones will be next week, unfortunately. So anyway, the Don Smith systems, we, instead of using spark gaps, we use these gas tubes, and they come in various amperages and peak amperages and voltages. So you can pick whatever you want. And so in this case, I've got a 470 volt spark over, and I'm going to be putting them in all the motors. The small motors will get ones that are about 90 volts spark over, and then these ones will get 470. Now I may tweak that as I look at it more, but I've been waiting to do this for some time, and it's just the list of 1,000 things that we can do to improve things, and there's only so much time in the day, in the month, in the year to incorporate all these new things, or the things that you know that you could do, and so that's one of the things that will be in with every kit. That's one of the reasons why some of the motor kits have been delayed, because I wanted to do that, and I also wanted to introduce something else here that we'll talk about in a minute. Anyway, so that's one thing, and that goes in the same place as the capacitor. They're in parallel with each other. So in other words, when it's starting to get up there in voltage, it will arc over and be a protection. And so you have the cap, keeping it mostly regulated, and then the spark over. So that's one of the things I wanted to mention. Of course, some people don't get it, but these are not meant to light up. When you're lighting it up, then you're going too high in voltage. So then you would need to increase your capacitance in that case. So some people, like with the little neon bulb, the kits that have the neon bulb will be like, well, my neon bulb's not lighting up. I was like, well, that's good. Because when it does light up, that means the charging battery is either not properly connected, or it's really got no capacity in it, and the system isn't seeing any load at all, or hardly any. So just because the battery voltage goes up doesn't mean you're actually really charging the battery, or like it doesn't indicate capacity. Voltage does not, unless it's voltage under resistive load that you know the value of, and you're measuring that over time, then you can tell the capacity that way. Anyway, so couple things here. One of the things that we have, getting back to this 10 coiler, is the double Hall system here. So the run Hall, which is going to be in position in this particular model, and I think I'll be doing this with all these recent orders and all subsequent orders, will be doing the double, for the big motor, the double Hall setup. The small one doesn't really need that. It really is not worth it to try and do that. But this one, what it is, and I've talked about this in the last motor videos, that we were showing the mini kit, or actually the larger, sorry, not the mini kit, the larger dual pole, which is more of the system I'm going to be promoting more than this 10 coiler. This has really been a burden to try and deal with. This is a very big motor and it's very awkward for me to ship it. So I'm more inclined to now make the 4-pole and extend it in extensions, layers, rather than try and promote this. This is pretty big, and we can't really get this rotor to be made thicker, which is what I've done with the 4-pole, which is really nice with that thick rotor, and the magnets are much bigger. This is what I can do with this 10 coiler for now. To make the rotor thicker would cost me probably another $1,000 on top of this kit. And who wants to spend that money? I know that nobody will be interested in spending that kind of money, even though I have lowered the price as low as I can make it. But anyway, going back to the Halls, the Hall sensor is a magnetic switch. It's a sensor switch, so it senses the position of a magnet. As soon as it becomes in the south pole of the magnet, the Hall face, in this case it's kind of the more rounded surface. It's not really round, but it's the face of the Hall faces towards the south pole. That's why we actually flip the magnets now, so that they're all facing the south pole up. So the bottom plate and the top plate, the magnets, the top side are south poles. Now we used to do the north poles before, and it's kind of really arbitrary, but we do that now because I can't position the Halls on the bigger magnets. I cannot position them between the rotor and the coils, and the coils ends up with their own pulsing, changing the magnetic field and messing up the Hall signal. So we put the Halls over top, and I use some of the 12 gauge wire as a hold here, and I double wrap it. So it's pretty good. You can reinforce it again with some more wire if you want, but it gives you the ability to move it around a bit. So I have the run Hall, which is on pin number 2, which should normally be that way in the regular setup. Actually, no, I'm wrong. Normally with the 1 Hall, it's on pin number 2, the white wire, and now it's on pin number 7. It doesn't really matter for anybody because we assemble, even in the unassembled kits, we assemble the Adreno part of these motors and in the mini kits. In the future we'll make a new board up here that's a more of a universal board, the green board, and then you'll be left to assemble that yourself once we have that all organized. But right now we only have the basic generic board that doesn't have any you know, it's just got holes everywhere and you have to use jumpers and all that. So I've never had customers put that together because it would cause too many mistakes. So anyway, it's always pre-assembled that way. And with this, we have this, the run hall is at top dead center approximately, and then this one is quite a bit retarded, so after top dead center, so that it, what happens is at startup, it has a different timing at low RPM. So what we do is we run it so long on the startup hall, and then after so many cycles that we determine, or so many pulses of the magnets, we switch over, and you'll see that when I start this, you'll hear a difference in RPM. It'll just go speed up. So anyway, that's again just a reminder of what we added some months ago as an option, which I'll make that permanent with these bigger motors. And then what else? So again, just the basics. We're running the Arduino gate driver and MOSFET gates off of this little battery because they need the isolation because of the spike. Even if it's, we don't want anything more than 12 volts on that positive terminal. And so we can't run it off of these batteries. If you attempt to do that, it's mostly the gate driver that's really sensitive, that can't have any kind of noise and spike on the line. So that's important. So now, these are not the correct batteries to run it off. We're going to be, I'm going to turn it down some, but it's going to be running at up to like 40-50 amps, and that's just not appropriate for these 35 amp hour batteries. You're going to see this is going to charge up fairly quickly. So this is sitting at 1212. It was sitting at 1207. I ran this very shortly, just before the video started, and it charged up a little bit. Obviously, in a few minutes, it's not going to charge up that much, but because, oops, this is sitting at 1290, 1289. So that one's pretty much fully charged, and the voltage drop will be significant because it's only a 35 amp hour battery. Now this is to me, it's pretty dangerous unloaded at full power level here, even at 12 volts. So if you're going to run this at 24, 36, 48 volts, then you need to start off slowly and turn down this little potentiometer here to do that. Now, what else should I say? You can extend the shaft lower and then run a load underneath. Like I've done that at times, put a pulley underneath there and run something. And originally we had this whole setup with a base and upright so that we could run loads off of the side. And that was just more expense, more parts, so we eliminated that. But you can still do the same thing with the holes. I just really didn't want all that extra inventory, and we originally made this motor so it could fit in a tube, actually, and stack it, but we never actually made the tube. But anyway, we have stacked it. You've seen videos where I've shown the 30 coiler stacked, and so it's about 450 pounds when you have the generator coils with them too, so it's a pretty heavy system. Now, okay, so now I want to talk about something else that we're going to be introducing. And so when we called, so these, so I got this homeschooler, some of you have met at my last meeting, who makes these, and they decided to call them RICs. Well, anyway, it's a resonance induction coupler kit, right? So this is known when they're being assembled as the RICs. Wasn't my choice, I had nothing to do with it, and so I thought it's kind of humorous. Anyway, so these are the RICs, and these are the mix. So this is not my choice again, but I like it. So this is the motor induction coupler kit edition. This is for the mini kit, and I'll be showing this next video probably tomorrow running. And so this is a really basic resonance kit. It's very similar to the third stage process idea, but it's not so, it doesn't really affect the rest of the motor so dramatically like the third stage process, which you could still use this for that as well, which would be on the output. So here's the output positive wire, and that's where we would put this if we were doing the third stage process. And yes, I've revealed this already. For those of you who haven't watched the videos, I've been waiting to learn that. This is one of the methods in the box that we can use. Now, the problem with doing that on the output side is it creates an enormous spike back into the input. And so this is where I couldn't really reveal this to everybody without really solving the problem with the semiconductors. And I tried to tell people that, but I knew what was going to happen. And knew this is why I only revealed it in my meetings, because I took 2 days to go over all the details, and I'm not going to go over all those details in video. There's many things I'm not going to share in video because there's no time, and people really don't care for my videos anyway. Once in a while, a good soul will tell me they like my videos, but most people hate the fact that I'm so long-winded, and I really don't care. I'm doing this for my customers and not for people who just want freebies. Nothing wrong with wanting freebies, but people generally on the internet, online, become rude and just say things because they have no respect. And that's just the nature of, everything becomes so free and easy that people start complaining about anything, even though they're getting it for free. Anyway, I do these videos for my customers, and I try and help them. I mean, I spend hours on the phone with people for free. I don't charge them for that, and I help them through video as well. That's what I'm doing here. So I knew that, like, what was that, 2-3 years ago when I did the Selfish Circuits, Loving Paths video series, and I first really introduced that then, even though we were already doing that for a couple of years in the mystery box, the black box, in Europe and in different conventions over here. But I decided to start showing that in the videos, and people were like, what is it? Some of them, people figured it out. Anyway, the point is that if I had shown that then and not solved this problem here with the capacitors across the MOSFETs, people would be maybe not damaging their transistors, because that's what we were using at the time, but they would be damaging them they would not just be blowing them out, but sometimes they would damage them, and then they wouldn't give you the proper charging, they wouldn't run right, and people wouldn't realize that, because people just want to try something and then they don't realize that they've damaged them. So that's where this capacitor and of course these gas discharge tubes are really helpful, because when you do this sort of thing, now you can protect the front end. But like even with my little demonstration model that still uses the transistors, I show at my meeting, I used to run that the whole time, which would switch around, and I've had several meetings I ran in where it didn't discharge the battery at all. So that has been shown over 2 days, maybe not always running it constantly, but I have shown that publicly, and I'm not trying to prove things really to people. I let them prove it to themselves. They can see every part. In that case, I wasn't showing, at the beginning I wasn't showing the coil and the circuits inside of the box, and then I started showing pretty soon on, early on, I showed a clear box, so you could see them both running together or separate. And so I still show that as part of my meetings, and I go over the details of that. It's kind of old news, but it's still new for a lot of people, and it's a way again to get more output out of the system. So there's a lot of different ways I've been showing over the years. You got the basic circuit, which is 2 outputs for 1 input. We talked about that recently, and I go over that in the book, with Don Smith's book, where when you spin an electron, you get 2 outputs for 1 input. This is revolutionary, but it's actually fundamental if you go back to the basic electron theory, and it's self-evident when you think about motors and generators. And when you when you electrically pulse an inductor, the electrons spin and they impulse first a magnetic, which in this case we're using to drive the motor, and then followed by an electric impulse. This always happens, and this is why Don Smith says, well, with the other meter I have around here somewhere, you can always measure, say this is a Gauss meter, you can always measure the voltage being produced by measuring the magnetic, the radiation, because that will, and at the square of the distance, you can calculate it without having to have expensive voltmeters and that. So anyway, every time you pulse a inductor, it gives off first, if you electrically pulse it, like we're doing here, it gives off first a magnetic, then an electric impulse. And that's what the electric side is, what's neglected in all these motor systems, and that's what we're using to charge the battery. And then if you magnetically pulse a inductor like you have in a generator, which is the opposite now, opposite kind of phasing, now you spin the electron in the same way, but first you have electric, then you have magnetic. And of course in the generators the magnetic side is completely ignored, and so that's what's, oh, that was one of the homework assignments in the next meeting for people. So if you're coming to the meeting, that will be one of the homework assignments. I'm kind of giving away some of the answer in this. So I don't hide things from anybody. I say them if you listen. I'm not going to beat you over the head and tell you to pay attention. If you don't want to, you don't have to. So anyway, so the basic system gets 2 outputs for 1 input, and that's more or less. And the reason why it can be more is that there's a heavy side component we talked about in these batteries that they're at right angles to the current flow. So if you think of this current flow, and the battery plates are like sails, and they're picking up this imaginary current that, of course, if there wasn't such a current, this meter wouldn't indicate anything, this clamp ammeter. But anyway, the bigger the batteries, the more you get. So you can get more than 2 output for one just by having a big, good battery. And then from there, with these capacitors, we're actually making the motor more efficient because we recirculate the energy back to the input, and then we also run it into the motor. So that becomes a more efficient motor in that case. So then the efficiency is better. So you're more than 2 than 1. And then then from there we add, if we do the 3 battery banks second stage process, then we can have roughly 3 outputs, more or less, depending on how well we tune this whole thing, which really is already pretty much tuned. But we can have, so doing like the Benita's loving path circuit stage 2, we can do that. And then we add the 3rd stage process, and that can be multiplied. And I haven't really revealed that. We'll do a product later on. It's not going to be this. This is not, in itself, wouldn't be sufficient. We have to have some safeties in there, and we have to deal with the changing load. And that's the hard part with that circuit. So that's going to be more specialized, but that creates unlimited output. You can multiply the energy out as many times as you want in that case. So this would be a prime mover, and basically I've had an agenda in the last probably 8 years to do all this, and it's just taken me time to attend to it because I have to make a living, and nobody's paying for me to do all this research. So, it's whenever I can. Anyway, I planned on doing this a long time ago, and so I've been slowly implementing these different things. And, I've been saying it all along. People haven't really been listening for the most part, because I said all these things more or less a long time ago, in different ways, and just only a few people here and there have said, hey, wow, that's right, it works. Anyway, so the other thing being, if we add this to the front end of the system now, which I'll be showing an actual example of that probably tomorrow in a video on the 4-pole mini kit, and that's what this is rated for. Like the gauge wire, we made it so obviously this is not, you wouldn't really want to run this system through this coil, and that's what we're going to do. And so what this does is it really doesn't affect the rest of the motor, and it's a resonant circuit, and in this case we want to load this down. So without the load you're going to have, well, I'll talk about that tomorrow. Anyway, this is the MIC because it's the motor induction coupler kit, because it will be a coupler kit. This is only one part of the kit, and but there's a big one there. You can see the toroid there, which would be a different kind of system, but it's similar. So what I've shown over the years now, over the last few years only, specifically this year, some of these things, is going from the basic kit to the stage 2 and stage 3, and then working back and doing the EMP coil. So, like I said, the magnetic output of the motor, the electromagnetic pulse, it produces an EMP, is an electromagnetic pulse, right? And so what we do is we charge the generator coils a little bit with that, and then I've shown, I have a model that I showed this year that I bring to my meetings and demonstrate, and that has the EMP coils around the outside, and so that absorbs some of that electromagnetic pulse that is just wasted energy that's radiating out. And it will go through those coils too. So you could add quite a few of them. And of course the same thing applies with like radio transmission, that the waves go out, or the fields and the waves go out, you know, at an angle, so you lose the intensity of those waves. And we are dealing with waves because this does oscillate at higher frequencies. I can see over 2.5 gigahertz radiation off of these coils. Now we don't charge batteries with that frequency because we don't have the suitable diodes here. These diodes will not accept that kind of radiation. But anyway, you can use these EMP coils around here and pick up more energy. And that's kind of the direction I'm going with the Don Smith system, teaching people how to basically pull this radiation that's all around them and use it. And when you use it coupled with the proper ground system, that's where it really makes a difference. Now, I haven't even shown how to apply the ground system. When you look at the book, you can apply the same thing to this book, to all the motors I've ever sold, and you can multiply the energy out that way too. So I'll get into that eventually with these motors, so people will be pulling the old monopoles off the shelf and realizing that they were quite a significant energy pump if you knew what to do. Of course, Bedini never told you what to do with all these options, and knew also about them, but didn't bother to really share them with people. So I have been sharing those things for 14 years, here and there. And then of course he deleted all the groups, so all those emails were gone. I have them all, but anyway, all these things were said by me, more or less. I mean, I didn't know everything like I know now, but I did share what I knew at the time as much as I could. Anyway, the other problem with sharing too much information is people get overwhelmed, and if they don't understand the basic circuit, which most people don't, most people who think they do understand the basic circuit don't. And I know this. I talk to people who are electrical engineers. Every couple of days I'll talk to an electrical engineer, a new conversation too. And you know, after talking to them, I can evaluate what they really know, what they don't. And I find that people don't know the basics, even though they know conventional, they know advanced things technologically, they're technologically advanced, conventionally speaking. They don't understand, unless they work in nonlinear application fields, then they're not going to really understand at least the capabilities, where to get the energy and what to do, because they're all into clamping it out, right? So I realized some years ago that we had to get back to the basics and make it simple, more plug and play. But I'm telling you right now kind of the options and that. So anyway, so you've got several different ways to amplify the energy, truly multiply it, and that's really not incorporating very much resonance into the circuit. We're not doing any real tuning here. We're taking advantage of what's called the ringing of the bell phenomena. So you can hear it oscillate. You pay for it once in a properly tuned resonance circuit. You can create, you know, with one input, multiple oscillations. And some rude person on my YouTube channel, and I don't tolerate rudeness, so if you're going to write something on my channel that's rude, I'm going to delete it, and I'm going to see it, so don't waste your time. But some rude person said to me the other day, well, you know, resonance isn't anything. Well, they didn't say resonant. What I was showing in my over unity demonstration wasn't really over unity. It was just such and such, whatever mumbo jumbo the guy spewed forth. Really, he didn't know what he was talking about, but what he's falling back upon was the fact that normally in a resonant circuit, you're not tapping into that multiplication of energy. Well, yes and no, you are many times, but you don't realize it is what I'm talking about. And people don't tend to expect to get more output than input. But really everything is already giving you that. I mean, really, so when you really define things, everything that we do is over unity in a sense. But according to people's certain definitions and expectations, the person didn't think that I had that. Well, you know, I can't help them if they don't really pay attention to the details. So, anyway, in a resonant circuit, you can tap that gain. And you can have higher voltage and amperage circulating, and then if you couple it and put it and output it the right way, and most people don't know how to do that, that's why they think there's nothing really significant about it besides tuning into radio stations, the bandwidth ideas. Well, you can, and that's the whole idea of the Don Smith systems, and that's what we're doing here with this battery. This battery is in place of a really tiny capacitor normally that's across the coil, which is then shorted out, or it's discharged through a resistive load and diodes and what have you, a snubber system. So now this is the place of the what we call negative resistance. This is the other body, as I talked about in my resonance book, and the multi-body system. Instead of a one-body system where you have one closed loop, and that's what everybody's used to. So they think, in a closed loop, you have Kirchhoff's laws, and everything is going to be a loss in that closed loop. But when you have a true open loop, which is this case, this is a floating ground. So this ground terminal, this is your return ground coming back to your positive terminal of the input battery. So this becomes what I call a multi-body system. There's a two-body systems that are not, they're independent of each other, and you have to have that for an over-unity system. You have to be pulling in the energy freely somehow. This is not forced here. This side is forced. This is your compression side. This is your decompression side. This is your positive resistance side. This is your negative resistance side. And this is not, there's a difference between negative resistance and negative differential resistance. And for those of you who critique me for using the term negative resistance, there's two different meanings to that. And the type that we're talking about, any of us who have talked about that as an over unity process, we're not talking about making our parts more efficient, so merely lowering the curve. We're talking about going truly below zero. And so now we are truly charging up this battery, in fact at the rate that this is discharging. So that's real negative, true negative resistance. And so, but this is what happens in it's kind of an undampened environment. So you have actually, you know, it's like you're winding up the electron on the positive side, spinning it up, and then letting it decompress, if you will. I mean, that's one way to look at it, as I talk about that more in the book. So that's the negative resistance side, and we have various other examples of that in this circuit, in this system, and all the potentials. So these motors are not obsolete with the Don Smith system. They're not they're not better or worse, because you can do all the same things with this. So we don't have to necessarily resonate the motor coils, but we can resonate in other parts of the circuit. And this just so happens to be the motor version, and the Benitez version that I'll be showing shortly in a kit, that will be when I get time to show that, which I will show that at the next meeting in November. There's only a few seats left too, so it's almost sold out right now for those who are deciding whether they want to come or not. And I'm not trying to push that. I can't physically have any more people than a certain amount. Anyway, the Benitez kit will be the same thing as this, but it will be without the motor, so you won't have torque, but you'll have the same kind of, you know, system here with its output, and the batteries will be maintained. And we're going to start off with the 4 battery system, and then we'll show how you can adapt the kit to a 2 battery system like the final patent. So that's another thing that's coming up. Like I said, we're going to be doing some hydrogen stuff with the resonance kit, and all that can be added to these kinds of kits, these motor kits as well. And the mix, we'll call the big one, you know, some funny name probably for the bigger motors, but that's a lot more involved to get that, because these are actually special resonance capacitors that we're using here. So we're not using just your regular capacitors to do that. Now, yeah, so there's a lot of different things that can be done with this. And so we can do now free mechanical or free electric, whatever you, well, we can do both free mechanical and free electric with these systems. Now we can also do that solid state, or and then we can do free heat as well, and that's one thing we'll get to. I was hoping to get that available for people for this winter, but the book just tied me up this whole summer, and it took longer than I thought. So all the types of energy that you need are done. So that's why I said the other video, that my work is done. Really, everything else is just kind of adding little accessories and making it more affordable, or more options. So I'll have to set this up. Let me see what my 10 times probe on there. Okay, so we're going to look at this. Not so concerned about the oscilloscope, but we're going to run this briefly here. It's not my object to show this running for hours on end, otherwise you won't be listening to me talk, and people are like, Rick, shut up, just show us just show us it, don't talk. And I really don't care for those videos where people don't say a word, they just try and show a picture, or you're kind of like, well, what's this about? Okay, so, although a lot of people do like that, but not me. Anyway, I'm going to start this amp meter here. Oops. And I'm going to want to look at it a little bit here, so I'm going to stand off to the side, because I just put this together, so I want to be careful about it. So I'm just using, of course, not the right color here, should be a red wire, but I'm just using a little jumper wire so that I can disconnect it if I need to. And you need a slow burning fuse on this, really, if you want, or not a fuse, or a circuit breaker, or a fuse that doesn't trip too quickly. Otherwise, when there's the pulse, it will trip. So usually there's a little bump when we touch the wires together. ding, you heard that there, and you can see it on the oscilloscope. So I'm just going to clip that. Now if you want really good output, use really thick wires here on your battery charging side, and that is something I talked about before. But so I'm just going to hook up the Arduino circuit, which takes a second to start up, and then this thing's going to start roaring. Now let me check the, forget what I left it at. Now you notice I covered up some of these terminals here because I don't want them touching each other and shorting out, so I've got one big one over the, so I'm going to start it lower, so hopefully we'll start up. I'm going to turn it down, then we'll crank it, because it goes right up to 50 amps if I have it up too high. So we're going to just start it, and it should self-start. And then see it, now it just jumped in to the start. So it went from the one to the other. There's your H wave. So we're looking at, I have it turned down, so we're about 18 amps right now. So it's going pretty fast, but I could turn it up faster. So 1365, because that's quite a bit of amps for this particular battery. So you can see the voltage drop. We're at 12 volts here, and I will turn it up now. So we're at 15 amps now that it's up to speed. So now we're at 29 amps, 28. That's just like cruising. I'm going to bring that back down. Makes me a little nervous. That's really fast. I mean, you can look at, those are 5 millisecond divisions. Between each peak pulse. So 5 milliseconds, whatever frequency that is. I don't have the frequency on there, but so now I've gone down to 13 amps. So you can see the voltage drop isn't as bad because I'm at a lower amperage. And then of course we're at almost 15 volts on this battery. Now that's under charge. So anyway, we can look at this, well, first of all, the thermal, infrared thermometer here. We want to look at the FETs. Now this has water cooling capability, which is not, I don't have the pump on here circulating. So hopefully everybody can hear me. I know I don't have the proper mic. I will get one. I did buy one, but I have to hook it up. My camera doesn't really work with the mic that I bought, so you have to bear with me. So you can see the spike and the oscillation. Now what we wanted to look at, so we're only looking at peak to peak. We're only at, oh yeah, we are at 500 volts. Peak to peak. be at that voltage. That didn't make any sense because that capacitor would not allow it to go that high. So let's look at this again now. Oh. So we're at 50 volts peak to peak. Yeah, okay, that makes sense. Like 60 volts, 62. So that's going to be very minimal charging because these capacitors are more for your 48 volt. But you saw right now, running this, now I'm running it a lot gentler, 13 amps. So let's just talk about this and I'll stop it so you can actually hear me. So you can see the waveform, and there's where the cap is charging and kind of oscillating a bit. Might as well show this with the camera up close. So you can see the oscillation. So you don't want to do too much oscillation there because we don't want the it really affecting the rotation. Like you have to consider. You have to consider the oncoming magnet. During the off time, you don't want to fight against the rotation of the motor. So it's kind of limited what we can do with the coils with this particular motor and like resonating them. They are pulsing. They are all cycling a little bit. So anyway, I'm going to turn this off. We can look at the voltages. And once the voltage is, once it's turned off, you can see it's 1261, and we'll see how much is charged up after a minute or two. We'll look at it again, and you'll see this one come back up, because it was dropping under load, and that should come back somewhat. So you can hear the at certain RPMs this thing really vibrates violently, and that's why I want to do the bigger rotor, but it's not a voltage or a RPM that really matters. There's two resonant points there. And of course under load you're not going to have that experience, but the 4-pole doesn't do that at all, really. So anyway, you can see the oscilloscope and get some ideas there and understand how this works. But yeah, this thing flies like crazy, and so really at 12 volts, like I said, you would want probably as low as 0.5 microfarad, and that way depending on, again, how much you load it down, because if you're going to run it really hard, like put a real big load on this thing, then you may have to increase that a little bit. I figure that most people will want to run at least 24 volts if they're going to spend this money on this. You can get a lot more out of it the higher the voltage you go, but you have to be really watching that, watching your temperatures of your MOSFETs. Even though these are high devices, you have to really properly install the heat sinks on them and then just watch them. These were not getting hot at all, of course, I was barely tickling them. I could have run, at that power level, I could have just run it off of one MOSFET. But I always do overkill on all of my products so that it helps prevent people's, and I know that some people will just never do the water cooling, and so I have to try and prevent that problem. So anyway, let's disconnect that. So let's take a look quickly at the voltages, and then, so you can see this is coming back up, 1272. Now that was running for a good bit of time, so it's going to have discharged that. Of course, that's still considered conventionally fully charged. And you can see this is 1240. That will come back down a little bit more, but it has actually charged up somewhat. So we'll just look at this voltage for now. So anyway, yeah, so that means, of course, I actually didn't want to have a lot of output in the charging into this little battery because it really can't take it. So it's better that I recirculated the energy with this big capacitor in the motor as we were doing. But if you were going to run this, you can run it, like I said, with these caps, but if you want to do it, it's easy to remove these caps too and put other ones in their place. And you could always create something like a switch where you switch between them. So one of my meters going off here. So anyway, you would really want to have, the bare minimum for this size motor would be at least a golf cart size battery bank, and that would be running it at low power levels. And then from there, you really typically, the way I intended this was for you to run like 1,000 amp hour batteries. So I would say really the minimum that you should have is your L16 batteries, which are like, 300-400 amp hour batteries at the voltage that you're going to run this and charge it at. And you want to do the same voltage input and output, more or less. That's really the way this is designed. And so, I mean, we have done in the hundreds of volts with these systems, and we've done that with the IGBTs. So we'll get into that eventually when we get time. So anyway, you want to have a big battery bank to really benefit from this, and if you don't, then you got to run this a lot lower because you're going to be damaging your batteries if you draw too much off of them. Like on these ones, these are sealed batteries, you're going to off-gas them, and then that's a problem. So yeah, you want at least golf cart or L16 batteries, but really 1,000 amp hours is, I mean, if you were to have this could be a, about 10,000 watt system if you go up in the voltage high enough. And that's the basic system. That's not adding all these other extras and extra processes that we're talking about. But on that level, with the generator coils and all that, you could probably get about that much. And but you would really need a big battery bank. If you had that much in solar system, you would have to have a big battery bank for that. And this requires two, so you can flip the batteries around, and then you have an additional output which you could have a third battery bank to charge up. So anyway, I've covered all those things before. I don't want to go off and repeating myself too much. So for any of the customers, you will see this now, and I'm going to show some pictures to the customers of the details here of how to connect things up and all that, which is what I'd already described, but for those who are trying to assemble it. So that's the motor, that's some of the updates, what we're planning for, and I think I've covered everything that I wanted to in this video. I don't think there's anything else left, but like I said, I'll kind of pick up on this video with the next one with the mini kit, and like I said, we'll be moving towards pushing the 4-pole rather than the 10 coiler as much. So I think we'll make this available if people still want it, but the 4-pole is more preferred, I think, for me to sell and make. And like I said, it's pretty much a done deal. I was considering changing the coils out, and these still work better than what we've tried recently, and I think we're going to stick with these coils. There's no need to change them. We can do all the other things. We can do add-ons to the existing system with these coils. They work fine. So that's it for now. I thank you for watching, and I hope you enjoyed it.